Today, we're going to be exploring an intriguing and hopefully thought-provoking mathematical operation called tetration. But before we get there, let's start with the basics and take a look at how we define some of our most fundamental operations. Let's start with multiplication. Back in elementary school, you probably learned that multiplication is just a shorthand for representing repeated addition. For example, when we say 2 times 3, what we really mean is add 2 to itself 3 times, or repeat the operation of 2 plus 2 3 times. A little later in your mathematics career, you learned what happens when you repeat multiplication. It's a bit more complicated than repeated addition, and we give it the name exponentiation. We write exponentiation as 2 superscript 3, and it means multiply 2 by itself 3 times, or repeat the operation of 2 times 2 3 times. Knowing that multiplication is just repeated addition, and exponentiation is just repeated multiplication, a logical question comes to mind. What happens when we go one level higher? What is repeated exponentiation? Ponder this for a second. It's probably not anything you've seen or thought about before, a level of generalization you hadn't even considered. I know I'd never heard of it before starting to make this video. Well, who would have guessed it? Mathematicians have already thought of this. They gave it the fancy name tetration, meaning the fourth repeated operation, addition being the first, multiplication the second, and exponentiation the third. And what do you know, they also gave a fancy name to this whole class of operations. They're known as hyperoperations. Now, let's dive into tetration and discover some of its properties for ourselves. First of all, how do we write tetration, and what does it mean? Let's take this example here. You can see that tetration is written very similarly to exponentiation, except that the 3 goes on the left of the 2 instead of on the right. The bottom number is called the base, just like for exponentiation, and the top number is called the height. In words, we would read this as the third tetration of 2, and what this means is to raise 2 to the power of itself 3 times, or repeat the operation of 2 to the power of 2 3 times. Except, this way of writing it in terms of exponents is a bit ambiguous. For a tetration, we want to start by evaluating the exponents at the top of the power tower. So, the third tetration of 2 would actually be calculated like this. Note that there's actually no consensus on how to notate tetrations. There are a few other ways, like Knuth's up arrow notation and iterated exponential notation, the latter of which I'll be using a bit later. For this video, I'm mainly going to be using this notation, with the height as the left superscript of the base. Let's play around with tetration a bit and see if we can figure out any sort of rules or laws. A pretty good place to start is using 1 as the base. It's pretty easy to see that any tetration of 1 is just going to give us 1, because 1 to the power of 1 is always just 1. You might also guess that tetration gets really big really fast, even faster than exponential growth. Even something as innocent looking as the third tetration of 4 turns out to be absolutely massive. For a general base x, we can see that the first tetration of x is just x, just like how x to the power of 1 is just x. And the second tetration of x is just x to the power of x. From the basic definition of tetration we established earlier, and by looking at a few cases, this rule follows. The n plus 1th tetration of x is equal to x to the power of the nth tetration of x. This is similar to how x to the power of n plus 1 equals x times x to the power of n. We can call this the recursive property of tetration. Do other properties of exponentiation also work with tetration? Let's try the commutative property. For exponentiation, this states that x to the a all to the b is equal to x to the b all to the a. However, this doesn't work for tetration. Here's one counterexample. This has to do with the fact that we can multiply in any order we want to evaluate an exponentiation, but like we saw earlier with the brackets, it does matter how you evaluate the power tower for tetration. So the commutative property does not hold for tetration. The distributive property for exponentiation doesn't hold for tetration either. It turns out there are a lot more limitations with how tetrations can be manipulated than with exponentiation. So far, we've only been dealing with integers in our tetrations. Using a non-integer base is pretty straightforward. We already know how to calculate exponentials with non-integer bases and exponents, and we can evaluate the tetration in much the same way as with an integer base. But how could we evaluate a tetration with a non-integer height, like, say, the 1/2 tetration of e? More generally, how could we approach extending the domain of tetration to rational heights? In the remainder of this video, I'm going to guide you through my problem-solving process for this problem, and my method for finding a value for the 1/2 tetration of E, and hopefully we'll gain some insight into tetration along the way. Let's start with a simpler problem that can possibly give us some tips and tricks for generalizing the tetration operation, generalizing exponentiation. Exponents only make sense as repeated multiplication for positive integer powers, so let's see how we can generalize the operation of exponentiation first to negative integer powers and then to rational numbers. Even if you already know how to calculate non-positive integer exponentiations, it's a good foundation for looking at tetration. Here's the equivalent of the recursive property for exponentiation. If we set n equal to 0, then we can solve for x to the 0 by basically doing the recursion in reverse, dividing. This gives us x to the 0 equals 1, and repeating this process gives x to the negative 1 equals 1 over x. We can continue reversing the recursion, dividing by x each time instead of multiplying, and in general, we get that x to the n equals 1 over x to the negative n. So now we can extend exponentiation to 0 and the negative integers. Let's try this trick with tetration. Again, we'll be using this recursive property for tetration we found earlier. Substituting n equals 0, we find that x equals x to the 0th tetration of x. To get the 0th tetration of x out of the exponent, we take the natural logarithm on both sides, to find that the natural logarithm of x is equal to the 0th tetration of x times the natural logarithm of x. Rearranging shows that the 0th tetration of x is equal to 1 for all x. Technically, this doesn't work for x less than or equal to 0 or x equals 1, but don't worry about that for now. Now, continuing this process, substituting n equals negative 1 gives this line, and we can substitute in the value for the 0th tetration of x that we just found. Now, once again taking ln on both sides, we get that 0 is equal to the negative first tetration of x times ln of x. So the negative first tetration of x is 0. But something funny happens when we try this process for n equals negative 2. Let's see. Using the recursive property and subbing in the negative first tetration of x equals 0, and we get 0 equals x to the negative second tetration of x. But we know that x to the power of anything can never be 0, unless x is itself 0. So it turns out that tetration is actually undefined for negative integers less than negative 1. This is quite different from exponentiation and all the simpler hyperoperations, where their domains are from negative infinity to infinity. Interesting. Okay, so now we've found the negative integer extension of tetration. Let's head back over to exponentiation to see how to find an extension to rational numbers. Here, we'll make use of the exponentiation power rule, which states that x to the a, all to the b, is equal to x to the a times b. First, let's set a equal to 1/2 and b equal to 2. On the right, we end up with x to the 1/2 times 2, which just cancels out to make 1. Now we can take the square root of both sides, and we get that x to the 1/2 equals the square root of x. Now, this result may seem kind of obvious, but what this tells us is that x to the 1/2 is equal to whatever we have to multiply by itself to make x. While this won't give us analytic solutions for most x, we at least have a way to approximate square roots of non-squares algorithmically, and this will work for fractions of 1 over any integer. At least we have an idea of what a fractional exponent even means. But what about other fractional exponents? Well, we can make use of the power rule again. This time, let's set a equal to 1/2 and b equal to 3. We can now replace x to the 1/2 with the square root of x as we just found, and now we have that x to the 3/2 is equal to the square root of x cubed. So we can use a numerical approximation for integer roots, along with the repeated multiplication of integer powers we already know how to do, to determine an arbitrarily precise value for any fractional power of x. Here's the issue. We discovered earlier that the commutative laws of exponentiation don't work for tetration, so this technique won't work for our problem. This is where the real challenge begins, deriving some sort of method to be able to calculate tetrations with rational heights. This problem is hard to sink your teeth into. You can't just start taking derivatives or plugging in values or anything like that, because the problem involves getting a grasp of the function itself, which we don't yet fully understand. So where do we even start? One strategy mathematicians often use when faced with a math problem is generalization. Oftentimes, expanding a problem to a broader scope actually gives key insights to solving the problem at hand, as well as potential extensions to other related problems. So how could we use generalization in this situation? Well, seeing as we talked earlier about the sequence of hyperoperations, it might be a good bet to try to generalize those. Let's invent a notation that looks like this: sub n a of x. What this is going to mean is that we repeat the function a of x n times, or in other words, we nest a of x inside itself n times. Don't mix this up with tetration, which I'm notating with the left superscript, as opposed to this nested function notation, which is the left subscript. So, as an example, let's take sub 3 x plus 1. We nest x plus 1 inside itself 3 times, so we get x plus 1 plus 1 plus 1, which turns out to be x plus 3. Let's look a little more in depth at another example. How about, say, a of x equals x plus 2. So our notation will look like sub n x plus 2. We want to see how changing the parameter n and the variable x affect the values we get after a of x nests inside itself. So I've created this table here. We have n changing along the top and x changing along the side. And now we can figure out the values we get for various combinations of x and n. The column for n equals 1 is easy. This just means we nest a of x inside itself once, or just a of x. Since we set a of x equals x plus 2 for this example, we can just pop those values into the table. Now, what about for n equals 2? Well, nesting x plus 2 inside itself once looks like this: x plus 2, which equals x plus 4. So that column is pretty easy too, and we can do the same for n equals 3. Now, how about n equals 0? This means nesting the function inside itself 0 times. Well, hopefully you can see the pattern that is started from n equals 1, 2, and 3. Keeping x constant, we can see that we add 2 every time we increase n. So we can just extend this backwards, subtracting 2 from n equals 1 to get n equals 0. And now we have that column done. We can repeat this for n equals negative 1 as well, and now the whole table is filled. Now, the whole point of doing this is that we want to find a general formula for the value we get out of this operator for a general n or x. And looking at this table, we can deduce that this general formula is sub n x plus 2 equals 2n plus x. You can check a few of the cases to see that this is right. It comes from the fact that we increase by 2 as n changes by 1, and we increase by 1 as x changes by 1. So now we have a general formula for this nested function notation for a of x equals x plus 2. How about a more complicated example, like a of x equals 2x? Again, we can fill out the n equals 1 column easily, as it's just 2x. For the n equals 2 column, notice that nesting 2x within itself once gives 4x, and for n equals 3, nesting again will give 8x, so we get these values for the table. To go backwards to n equals 0, we divide by 2, again, the opposite of multiplying by 2, and we can do this again to get the n equals negative 1 column. So this table is done just like that. Identifying the general formula is a bit trickier this time, but it turns out to be 2 to the n times x. You might notice that when we did this nested function notation on addition, it spat out multiplication, and when we did it on multiplication, it spat out exponentiation. Keep that in the back of your mind, it will be useful later. Before we continue, let's go over some of the rules for our nested function notation. We saw that when n equals 1, we just get a of x right back. And when n equals 0, we took whatever n equals 1 was and just did the inverse of a of x. So we end up with x all by itself. We also have this iterative rule that sub n plus 1 a of x equals a of sub n a of x. This comes from how we defined the nested function notation. Lastly, we have this very important rule. Sub m a of sub n a of x equals sub m plus n a of x. This one is pretty intuitive. As an example, if we nest 3 copies of a function inside 2 copies of that same function, there will be 5 copies of that function in total. The iterative rule we just saw is actually a special case of this rule, where m equals 1. Now we have all the tools we need to tackle the last of these tables we're going to solve. Remember how nesting addition gave multiplication, and nesting multiplication gave exponentiation? This makes sense because the nested function notation was supposed to help us generalize these hyperoperations. So if we want to analyze tetration, we'll need to nest exponentiation. So let's try that now. In particular, let's look at sub n e to the x. Using the rules we just found, we know that n equals 1 is just e to the x, and n equals 0 just gives x, so we can fill those ones in just like that. Now, for n equals 2, nesting e to the x inside itself just gives e to the x. I'm going to put it in the table in this form, just so we can see the pattern more easily. For n equals 3, we just have an extra e in the power tower. Starting to look familiar? Alright, now we also learned that moving back an n is the same as taking the inverse of the original function, which in this case is the natural logarithm of x. So for n equals -1, we just get ln of -2, ln of -1, and so on. Now, there's two things to note about n equals -1. First, you'll see that I didn't fill in x equals 0 for this column. That's because we can't take the natural logarithm of 0 to find this value, just like how we couldn't find the negative second tetration of x earlier. The second thing to note is that the natural logs of these negative numbers are going to be complex numbers. I'm not going to talk about complex numbers today, but it won't matter that much where we're going anyways, so just ignore the fact that these are not real numbers. Before we find the general rule for this nested function, we're going to need yet another notation. I'm going to use one of the notations I mentioned at the start of the video, the iterated exponential notation. So for this example, what this means is we raise e to the power of itself n times, with an x right at the top of the power tower. Notice that if we set x to 1, then this is precisely equal to the nth tetration of the base, in this case e. Now we're ready to find the general rule. Since I've left these in their exact forms in the table, hopefully you can spot that the row for x equals 1 looks an awful lot like the sequence of integer tetrations of e, and the other rows are just the same sequence but with the top e raised to the power of x. So I claim that sub n e to the x equals x base e to the n of x. Like we just saw, x equals 1 in the iterated exponential just gives the tetrations, so this checks out with our observations of the table. I'm not going to prove this, but once again, feel free to check the numbers in the table and see that everything else checks out. So we have a way to write tetration in terms of this nested function notation. Now we need to see if we can find some sort of equation that lets us get a sense of tetration. Here are the two equations we'll need, the compounding rule of our nested function notation, and the formula we just found from the table. Let's set both m and n equal to 1/2 in the first equation. When you take m plus n, you get 1, so sub 1/2 a of sub 1/2 a of x just equals a of x itself. Now, let's set a of x equal to e to the x. From our second equation, we know that sub 1/2 e to the x equals x base e to the 1/2 of x. So we can replace sub 1/2 a of x with sub 1/2 e to the x, and then replace that with x base e to the 1/2 of x. Now we have x base e to the 1/2 of x base e to the 1/2 of x equals e to the x. We're so close. Now, recall that when we set x to 1 in the iterated exponential, we get back a tetration. So if we can find a function for x base e to the 1/2 of x, we can set x equal to 1, and the output will be precisely the 1/2 tetration of e. So now our problem becomes finding the function, let's call it f of x, such that f of x equals e to the x. This is reminiscent of how finding the 1/2 power of x, or in other words the square root of x, was equivalent to finding the number which, when multiplied by itself, gives x. In fact, this function f of x is actually known as the functional square root of e to the x. We've definitely made progress, but we're not done yet. To find this function f of x, I'm going to use a very powerful mathematical tool known as Taylor series. Truncating this infinite polynomial series at a particular point gives us an approximation of the function in question, and this is often a really useful tool because polynomials are much easier to work with than, say, trigonometric or exponential functions. I'm not going to get into where this series comes from, but the main thing you need to know is that we can approximate functions in this way, and that this is the Taylor series for e to the x. Elegant, isn't it? Now, we're looking for f of x equals e to the x, so we can replace e to the x with this Taylor series. How does this help us? Well, let's replace f of x with the Taylor series too. I'm going to use a simple second-degree Taylor polynomial to demonstrate what we're going to do. Let f of x be a general second-degree polynomial, a plus bx plus cx squared. To get f of x, we nest f of x inside itself by replacing all the x's in the equation with copies of f of x. expand out the squared polynomial, distribute, and group terms by the degree of x they have. I've just thrown away all the terms with degree higher than 2 because we won't need them for this approximation. And setting all this equal to our Taylor polynomial for e to the x, we get this line. Now, we set the coefficients for corresponding powers of x equal to each other, like this. Now this is a system of equations with 3 equations and 3 variables, one that we can solve. Or really, we can get the computer to solve it. And here's the result. A equals 0.4979, B equals 0.8781, and C equals 0.2618. So f of x is approximately equal to 0.4979 plus 0.8781x plus 0.2618x squared. And f of 1 is approximately equal to 1.6378. Now, recall that f of x is a shorthand for exp base e to the 1/2 of x. And we found earlier that exp base e to the n of 1 is equal to the nth tetration of x. And finally, we just found this approximate value for f of 1. So we can conclude that the 1/2 tetration of e is approximately equal to 1.6378. We've done it. We found a way to extend tetration to the rational numbers, or at least 1/2, just as good. But how close are we to the right answer? The accepted value for the 1/2 tetration of e, found by much more efficient methods, I can assure you, is around 1.6464, which gives us a percent error of 0.52%. Not bad. But wait, this was just using a simple old degree 2 Taylor polynomial approximation. What if we go further, using a higher degree polynomial to get a more precise answer? The expansions of those nested higher degree polynomials get pretty tedious, so I wrote some code to do it for me. So here's what we get from a degree 8 approximation. I had to add more decimal places because this approximation is just so good. Check this out against the accepted value. Percent error of 0.0000035%. That is pretty darn close for this little Taylor polynomial approximation. And by the way, here's what f of x for the degree 8 approximation looks like, plotted against e to the x. F of x is in green and e to the x is in blue. And you can see how close they really are, at least in the vicinity we care about, which is near x equals 1. Let's recap what we did to get here. We discovered tetration as a natural extension of the hyperoperations, the repeated operation of exponentiation. We found some of the properties of tetration, and in particular that it did not have as many in common with exponentiation as we might have expected. In search of an extension of tetration to the rational numbers, we tried looking at how exponentiation is extended to the rational numbers, but these techniques did not directly apply to tetration. Then, we invented a new nested function notation to generalize repeated or nested functions, and discovered some of the properties of this notation through analysis of tables. Finally, using some of the properties we found, we used Taylor polynomial approximations to find a value for the 1/2 tetration of e to a high degree of accuracy and precision. Was this the most efficient solution? Not exactly. Does it allow us to find general tetrations of rational heights? Well, we could go through the same process, but nesting f of x inside itself 3 times, or 4 times, or n times to get the 1 over nth tetration of any base b. However, for n much larger than 2, this would get fairly intensive to calculate accurately. But did we get an answer? Yes, we did. And did we learn a lot along the way? I think so. In terms of tetration itself, I think this gives a lot of insight into the operation, how it works, and some of its limitations. It also gives us some ideas of how we could proceed to a more complete and general solution. I know that working on this problem sheds some light on techniques we can use when solving tough math problems, like generalizing to a broader set of cases, or comparing to something you already understand. I hope you got a sense of these ideas from watching this video.